Thank you very much. Well, okay, I'd like to share with you some of the thoughts of a, say, practicing physicist and a mathematician, not a philosopher. Well, okay, so it will be about space-time. But let me first start with a... Okay. Yeah, okay. Well, in everyday life, when we usually say about something that exists, we usually refer to something that exists in space and in time. Of course, this applies to concrete physical objects like this chair, this book, this conference, and so on, not to the abstract ideas like, well, science itself or love or friendship. Well, and this is mainly because we are local objects ourselves. We live in space-time and we cannot help it. And of course, that's also reflected in the languages we use that, well, they have tenses, they have aspects. So this, especially this time aspect is present there. You can adopt different philosophical standpoints about what actually exists. You can, well, adopt this viewpoint of presentism, saying that, well, only the things that happen now exist. And of course, this surface of now, it's constantly evolving. You can say that, well, what happens now exists, but what happened, well, that happened, so it exists also. Or you can say that, well, I have a kind of block universe and it's all eternal and it always exists. Okay, but how about the space and time themselves? Is it only an abstract idea or is it just a physical, or is it a physical object? Well, Newton said that space and time are absolute. Leibniz, on the other hand, said that, okay, that's a relational concept. What really matters are the relations between objects, not space itself. For Kant, space and time were synthetic a priori, so non-empirical objects. But all that happened before, well, at the time where only one geometry was known. It was the Euclidean geometry. Then came the revolution, particularly by Riemann, who showed that, well, in space you can have many different structures, many different geometries. And then Einstein showed us that this geometry is physical because it's gravity, and gravity is certainly something that we feel. Okay, so that's about classical physics. Now, in quantum theory, well, you all know that quantum theory has troubles with ontology on its own. And when we try to apply it to space-time physics, that can get even more tricky. You can ask the question, is the space-time itself quantum, and so what for the philosophy? Okay, but let me start with the, okay, let's first talk about operational paradigm in physics. That's a method that prevails particularly in quantum physics. So instead of asking what the world is really like, we ask the question, what can we measure? And then what can we infer about the world from what we have measured? So in this spirit, you can adopt a radical point of view and cut out everything that you cannot measure. So if something cannot be measured, then it should not exist as a physical entity. Of course, it can exist as a mathematical object, some abstract thing, but not as a physical entity because we cannot access it in any reasonable way. Of course, this creates some tension between epistemology and ontology because, say, in the usual point of view, you would say, okay, there is some external thing that I want to explore. So you first make an ontological statement and then you try to learn something about it. So you do the epistemology. Here you can see it the other way around. So you first ask, okay, what can I learn? And then what comes out of it? And what are the ontological implications? So that's a bit in the spirit of Quine and the ontological commitment. So the things that a given theory need to exist. But as far as I know, the problem with Quine is, first thing is that strictly speaking, you would need to formulate the whole theory in first-order predicates. So phrases like there exists x such that f of x. And that is, of course, not the case in any reasonable physical theory. So you would need to use a kind of extended argument, which means that you would need to paraphrase your theory. And that's, of course, it's certainly non-unique, etc., etc. The other point is that if you use Quine's criterion, you will not know whether the existence you are talking about is really in physical world. It might well be that it just implies the existence of a theory, but it's a purely mathematical construct. Okay, but let's see it on the examples. So let's start with the classical physics, with general relativity. So the important point about general relativity, and actually all of classical physics, is that the observer does not influence the spacetime. Okay, we are just on a stage and we look through it. Can you formulate the GR in operational, from an operational standpoint? Well, you can, and there's a nice paper by Eller, Spirani, and Schild, and I thank Michael for drawing my attention to this nice article. So the idea is roughly the following. You start with a set of events, just a set of points. Then you have a second set, which are the histories of the light rays. And then the third set, which are histories of massive particles, observers, if you wish. So you start with just a set. Then you can impose some differential topological structure, which you can justify to some extent by invoking the idea of measuring signals and some echoes, etc., or some stability against perturbations. You can get the smooth structure. Then you can either have a projective structure when you use the histories of massive particles, or you can have a conformal structure, which comes from the histories of the light rays. Now, if you want to make them compatible with each other, saying that, okay, any light-like geodesic should also be light like in this conformal structure, then you have some compatibility condition, and this gives you a Weiss structure. And to get the metric structure, you need yet another small axiom, and then you get to the final theory. So in principle, at every stage of this procedure, that's the argument of Eller, Spirani, and Schild, you have some assumptions about physics. And in principle, you can test them. And you can see if, for instance, the equivalence principle is valid or not. That is actually being done in some of the space experiments. So in principle, you can formulate it in an operational method. But in practice, that's not what you do in GR. You don't measure the space-time metric and draw information out of it. I mean, even if you look at the evolution problem, if you have some experiment, you take an initial state, you prepare it very precisely, then you launch the evolution, you measure, and then you infer something about the theory. See whether it's correct, you fix the parameters, etc. But of course, in Einstein equations, you don't impose the data on a Cauchy hypersurface. We don't have a whole Cauchy hypersurface here around to make the experiments. You rather do the observations. So the procedure is that first you fix some context. And this means that you impose some high symmetry of the problem. So whether we're considering planet Earth or the solar system, or are we in a cosmological context, we impose some symmetry, like spherical symmetry or isotropy or whatever. And then you have some free parameters, try to solve the equations, and you compute the parameters as, for instance, you do in cosmology. Right? You assume a certain model, lambda CDM, you compare it against the observations, and then you fix the parameters, the content of dark matter, etc., etc. So that's not really operational. You first make an assumption that my universe is FLRW, for instance, of course, in some approximate sense. And then you try to fix it and then maybe improve it. Okay, so let me make some points about what we can actually observe. Now, imagine that we are just in Minkowski spacetime. So we have conformal future infinity here, conformal past infinity here, and that's our word line. We were born here, and here we come to an end. So the best of the universe we can ever observe would be this region here. And now if we have learned something, we want to publish it and make it public to the outer space, then we can only reach our potential readers who will sit in this part. If we want to make experiments, so send something and get information back, well, we have only this compact region of space at our disposal. So as you see, if we have a finite lifetime, there are some blank space, even in flat space-time. So, of course, you can ask the question, if you adopt an operational point of view, saying, well, okay, can we say that this part of the universe exists? Because we can never get any information there. We can never access it. Well, in an expanding universe, that's even more troublesome. And especially if the universe is de Sitter, as we supposed to be from the observations, because then we are not only constrained by the speed of light, so the internal speed in our space, but there's also the velocity, the recession velocity, which is not a velocity within the space, but it's the dynamic of the space itself. And it has some drastic consequences. In particular, some of the objects that are at high redshifts, well, they are actually receding with a velocity that, well, if you take it literally, it's greater than c, greater than the speed of light. But it's not the velocity within the space. It's the dynamics of the space which causes it. But the effect is that these distant objects can be as far as 40 billions of light years from us right now. But the more drastic thing is that even if we go all the way up to infinity, we have an infinity of time, this diagram is complete in this direction. So that's the true infinity here. Well, the furthest objects we can ever get information from would be from around 60 billion years. Which means that if our universe extends beyond this point, we can never say what's there. Now, usually in cosmology, you adopt the so-called the cosmological principle, saying that, well, if I move to another galaxy, I should roughly see the same space. Well, that sounds reasonable because, I mean, why should we live in a special place? But of course, that's an assumption. That's an assumption you cannot tell the difference, at least not within these models. So again, you can ask the question, well, if the universe is in particular infinite, can we even say that it exists beyond this point? Because, I mean, even if it does, then it has absolutely no influence. And that's one of the problems with the multiverses, for instance. If you can say, okay, there might be different universes, but there's no chance they interact in any way with us, so why should we bother? Okay, there's one interesting possibility that I'd like to point out is the Penrose cyclic cosmology, which gives a bit of a different point of view. Because Penrose says that, sorry for the Polish subtitles here, but the idea is that Penrose says is that you can actually extend your space-time through the scry or through the Big Bang if you want, and you can glue these diagrams one after another. So that would be the picture, and you have a crossover surface instead. Well, that's hypothesis, of course. Penrose says that if it is true, then we can get the signals. As you see, the light cones, they extend through the crossover surfaces. So in principle, if we wait long enough to another eon, we can see the whole universe, arbitrarily far away. And Penrose says that, well, indeed, right now we can maybe witness some signals from the previous eon. The effect would be that the gravitational waves that were emitted by the collision of supermassive black holes in previous eons would leave footprints on the cosmic microwave background in our eon. So whether this is true or not, that remains to be settled. I think Professor Meissner is working hard on that. But it's an interesting point for me, because it gives a different picture from this one. Because here you can really see the whole universe, at least in principle, if you wait long enough. But okay, of course, one has to be conscious of the fact that the signal that gets transmitted, it will be very different. It's not as simple as just a photon flying through, but it gets transformed. So we really have to know how to recover this signal. Okay, let me now go to the quantum theory. Now, to me, the biggest difference and the upshot of quantum theory is that here the observer does influence the observed object. So let me describe the Heisenberg microscope for you, which to me is the essence of quantum mechanics. So Heisenberg tells us that, okay, if you attempt to measure particles' position with some precision, then you necessarily disturb particles' momentum. And you can do some heuristics, you can do some computations, and then you arrive at this kind of uncertainty. She says that, okay, if you want to measure with a great precision, then you disturb momentum, and the product of the two uncertainties is always bigger than some fixed number. Now, if you say, okay, how can I realize this object within mathematics, then you discover that you are bound to use non-commuting operators rather than just numbers. And that's non-commutativity. On the other hand, if your algebra of observables is non-commutative, well, you discover that there exist states which are not just tensor products, but not simple tensors, but sums of it. And this is precisely the entanglement. So to me, that's the essence of quantum mechanics. Well, as Pavel said, particles' properties do not exist before measurements. And if you consider quantum field theory, you say that, okay, even the particles do not exist before we measure them. But on the other hand, quantum mechanics not only gives you the possible outcomes, but it also gives you the odds, the probabilities. So it's more. It's not that you have a photon and you only know that it can be polarized like that, or spin up, spin down. But the theory really gives you the odds. It says you that if I make an experiment with such and such probability, I will get this answer. With other probability, I will get the other answer. So to me, the probabilities are also a real thing, because it affects the outcomes of your measurements. Let me also point out that quantum mechanics, as it is, doesn't really care if we interpret it or not. I mean, it gives us the tool to compute the probabilities, and that's it. It relates to the experiments, and it doesn't really care whether we believe that the wave functions exist or not. We don't need it to make the computations. But now, quantum mechanics is itself embedded in spacetime. Let's first look at non-relativistic quantum mechanics. Well, we need the existence of an external time parameter. We have a Hamiltonian evolution. We need some external parameter which does not come from quantum mechanics. It comes from somewhere else. You can say, okay, but how about the space? Is it superficial? Sometimes you can find a slogan that what matters are only the correlations. So it's a bit in the spirit of Leibniz, saying that it's only about the relations, not about the true positions in space. You have some tools to interpret it, like the directed acyclic graphs. You have also some approaches using so-called boxes, saying that, okay, I just have a box which, well, it gets some input, and it gives me some output, and I don't know what happens inside. And well, in this context, you can derive some other, so post-quantum theories, which gives you some other correlations, which can be even stronger than quantum. Okay, but my point is that all of that actually takes place in space-time, whether we like it or not, but that's how it is. Why? Because our experiments are always local. Because we are local, we live in space-time, here and now. If I make an experiment, that's always here and now. That's the only way I can do. And moreover, the outcomes of my experiments, they are always local. Whatever weird quantum theory or post-quantum theory I will have, at the end, I need a number. I need a 0 and 1, some classical information. Now, moreover, the physical quantum systems, they need to respect the causal structure of the space-time. On paper, you can write any Hamiltonian you wish, but if you go to the experiments, you need to be sure that this Hamiltonian does not give you some superluminal propagation of information, because we don't observe such a thing. So the space-time structure, it is hidden there. We just typically ignore it in, say, relational approaches. But it is there, and it is expressed, for instance, in the demand of no signaling principle in quantum mechanics. Okay, so we tried to do a bit of mathematics behind it, to model these things with Tomek Miller, and now we're also trying to push it forward with Paweł and Ryszard Holodecki. So the rough idea is to consider so-called potential events. So we model them by probability measures on the space-time, and that's an object which lives on the space-time. So it encodes, it has some support, which can be the whole space-time, so it gives you the odds. It can be here or there. But then it has also some probabilities. So we have both of these features included. Okay, so let me elaborate a bit about non-locality, because that's also a slogan that appears in quantum mechanics, that quantum mechanics is non-local. Let's consider first a classical experiment. So imagine I have two balls, and a green one and a red one. Well, I close my eyes, I mix them, and I put them into black boxes. I don't know which one is where. And then I throw the boxes with, say, the speed of light, or very, high velocity. And then I'm Bob, and I have a friend, Alice, which lives, for instance, in Andromeda. And I ask Alice, okay, let's play a game, and let's check out who gets the red ball, who gets the green ball. So, but before we check, we don't know what's in the boxes. I don't know, Alice don't know. So we need to write this state as 1/2 Alice green, Bob red, and 1/2 Alice red, Bob green. Okay? And once I make the measurement, it collapses. Of course, if I'm Bob and I look at the ball, I open the box, I see, okay, it's red. Then I know immediately that Alice has a green one. And obviously the other way around. If Alice knows, she knows immediately that Bob has one. But of course, you would not say that in this situation you had any information transfer. That's nonsense. That's just the odds. That's how it is. And okay, if you look at the EPR experiment, in this context, that would be just the same. Imagine that you have just two particles, spin up and spin down. You make the experiment. Now, instead of green and red balls, you have spin up and spin down particles. Bob measures, and then it collapses with an Alice. If Bob measures up, then Alice is down, and the contrary. So we have the same correlation. But of course, there is more in quantum mechanics, obviously. So imagine now the following situation. If now Bob is a bit of a cheater, and he says to Alice, hey, look, I have hidden in this box a yellow and a blue ball. And let's do the experiment. You go to Andromeda, and then we measure. And then what Bob did, before he opens his box, he put the box through some machine, and the machine colors the balls. If it was red, then it will be yellow. If it was green, then it will be blue. And then they measure, and then, of course, the table is trivial because Alice gets surprised, and she said, well, I had something green or something red. It's neither yellow nor blue, so I have, well, this does not make any sense. But if Bob tries to do the same trick with the entangled particles, and now if you imagine that, okay, green and red was, say, the basis up and down with the spins, and now Bob puts a polarizer, and he says, okay, but now I will measure in another basis, say plus and minus. Then this operation, this Bob's operation, does affect the Alice state also, and the correlation will survive. So to me, that's the difference between quantum mechanics and classical. So it's the non-locality is not about this kind of collapse within the measurement, because we can have it also classically. It's about this action, spooky action at a distance, which is not an action strictly speaking, because it cannot serve to transfer information anyway. Okay, so that's my view on quantum mechanics. Now, the important point is to realize when and where do the correlations actually exist. Because if you say that, okay, there were some correlation between the things, then you implicitly assume that Alice and Bob have met. And for instance, here they met, and Bob said, oh, sorry, I changed my mind, I colored the balls, and the experiment was nonsense. But if they don't meet, then Alice don't know what happened, whether she got the wrong answer or what. And the same for quantum. If there is some correlation, well, they should witness this correlation. If you look at the spacetime diagrams, well, let's first do it in Minkowski spacetime. So here's Alice, here's Bob, and they have their future light cones here. So the correlation, to me, they should live somewhere here, so at the intersection of the two future light cones. And it might well be that Alice chooses some path going here to infinity, and Bob can never get to her to check the results. So the event C might not happen if they don't meet. But the situation is even more drastic if we're, for instance, in a black hole region, so under an event horizon, which, well, might be. We have some supermassive black holes. We might as well fall under a horizon. And if they do the experiment, well, they will never get the chance to compare their results. So the event C does not exist. It's not within the spacetime. So would you say in this situation that the correlation really exists? Because, well, theoretically on the paper it exists, but no one can even check it. Okay, so let me make a few remarks about quantum field theory, which is supposed to unify the quantum principles with the spacetime itself. And indeed, any theory of quantum fields begin with the sentence, let M be a spacetime, classical spacetime. That's something to start with. Whether you do second quantization or path integrals or any algebraic approach, any reasonable axioms of any reasonable quantum field theory should at least assume Poincare covariance and microcausality, which are related with the classical spacetime structure. And this you can impose it in many different ways. Either you impose some commutation relations on your observables, or some supports of the propagators, or something on the correlation functions. Anyway, the spacetime is classical in quantum field theory. So a measurement in quantum field theory always involves an annihilation of a particle, even if that's a weak measurement, because you can say, well, if I have a photon going through the bubble chamber, well, I don't destroy it. But you don't destroy this photon, but you need to record something else, some photon triggered by this one, whatever. But at the end, you need a number, and the number can only come if a detector clicks. For a detector to click, you need to absorb something, annihilate something. So to me, the fundamental non-commutativity in quantum field theory is the non-commutativity between the annihilation and creation operators. And well, the correlation, in a sense, they sit in the quantum vacuum. Okay, well, in quantum field theory, actually, there are several problems with the ontology. Well, usually we are bound to use the notion of a particle. But what is an elementary particle, actually? First thing is that you have a Riesch-Schlieder theorem, which tells you that particles can never be strictly localized. It will have always have some exponential tails. And it's throughout the whole space-time. It's not only on the time slice, it's throughout the whole space-time. So how can you interpret it? Because after all, when we measure something, it's always local. So do the local experiment, although your states are non-local. Second point is that particle states exist only asymptotically. If you have an interacting quantum field theory or a quantum field theory in a curved space-time, then typically these particle states, they only make sense asymptotically. And of course, you can have quantum field theories with no particle interpretation at all. There are some conformal field theories, for instance. But there's even a more drastic problem about the existence of the quantum field theory itself. Because, well, what we would like at least to know that something exists as a mathematical entity. And that's known in classical physics. That's assured in non-relativistic quantum physics because, well, wave function is a well-defined vector in a Hilbert space. But if you go to a quantum field theory, we don't actually have a satisfactory mathematical structure behind a satisfactory quantum field theory. Of course, you can construct quantum field theories in, for instance, 2 dimensions, 3 dimensions, or just a free quantum field theory with no interaction, and then there's a sound mathematical structure. But if you do quantum electrodynamics, well, the structure is at best incomplete. We don't have the good mathematical description. So can we say that in what sense it exists? Within mathematics even. But then you say, well, okay, maybe it doesn't exist in mathematics, but it is still in perfect agreement with the experiment. So there should be something physical behind it, something that exists. Okay, so we make a point that usually we believe that, well, okay, it's just a technical problem. We're just not smart enough. We don't know enough of mathematics to have a good quantum field theory described, but that will come one day or the other. That will be settled. But maybe it's not that. It's not so, and that's some result from 2015. It's called the undecidability of the spectral gap. So these 3 guys, they consider the problem of the existence of a spectral gap in a Hamiltonian on a lattice. So you have some material, and you want to know whether it's an insulator or not. And this depends on whether the energy levels, there's a spectral gap in the energy levels, or whether it's a continuous band. And they showed that if you consider things on a lattice, then this problem is undecidable in the strong sense of Gödel theorem. And of course, that's very interesting. That was published in Nature, because the big thing is about the spectral gap problem in quantum field theory, which is one of the millennium problems worth $1 million. But it might be even more drastic. Maybe it is that, for instance, the convergence of a perturbative expansion is an undecidable problem. Maybe something like this happens, and we would need to live with it. Maybe it's like that. Okay, so let me now pass on to the idea of a quantum spacetime, which is a bit different from what we heard about quantum gravity from Klaus' talk. So here, let me now describe for you the Doppler-Herford-Hagen-Roberts microscope. So they say that, okay, if you try to attempt to localize an event in space-time, well, if you want to do it very precisely, you must use very short wavelengths. But if you do so, you pump a lot of energy in a very tiny region of space-time, and then according to the principles of GR, there will be a gravitational collapse, a trapped surface will form, and eventually your information will be hidden under an event horizon, so you will never access it. So these heuristic arguments would lead to an uncertainty relation between the measurements of space-time positions, for instance, between time and some space coordinates. And again, these cannot be usual numbers. These needs to be operators which do not commute. So this leads to the idea that the algebra of observables of the spacetime itself is also a non-commutative algebra. So let me stress that this quantum spacetime hypothesis, as put here, is a consequence of the classical general relativity. There's nothing more here. No new principles allowed. But what's even more interesting, that this spacetime, quantum spacetime, has a geometry. Sometimes it's called a non-commutative geometry, but still it's a geometry. So here the philosophy is radically different from quantum gravity, because you do not attempt to quantize the geometry, but you rather look into the geometry of the quantum. And for instance, the difference is that that's something we proposed with Nicolas Franco, and was developed in several papers, that the notion of a causal structure in such a quantum spacetime can be rigid. So it's not like the light cones are blurred in a way, but although your spacetime itself is blurred, your events are blurred, but the causal structure is rigid. And the question whether two events in such a spacetime are causally related or not is still a yes-no question. So okay, that is an option. Well, let me conclude with some, say, final remarks about the Heisenberg cut, which I already discussed yesterday. So whenever you do any observation, you need to divide the world into a system and an observer. I'm the observer, I observe the system. And this means that I actually make a cut between ontology and epistemology. The system exists, I explore it, and so I do some epistemic statements. Putting it in the words of Bohr, we must be able to tell our friends what we have done and what we have learned. The mathematics of the operational paradigm tells you that, okay, in the most general form, you can consider the algebra of observables, whatever big you wish, and the space of states. So this has an epistemic flavor, the observables, and the states of the system, they are independent of your observables, so these have an ontic character. But also the point is that mathematics tells you that once you have fixed your algebra of observables, you can completely determine the space of states. All of the states of the system are determined by your observables. So it's also, to me, in this Quine spirit, because once you have the things that you can measure, it tells you what exists, are the states of the system. But, of course, there's always some but. Well, first of all, some states might be unphysical, and that's typically seen in quantum field theory. You have a big algebra of observables, but then you see that some of the states have infinite energy, for instance, or have some really nasty unphysical properties. So you want to discard them. So you say that, well, not all of the states are realized in nature. These are unphysical solutions that we know this argument. The other point is that the choice of the very choice of the algebra of observables always requires some presumptions, because we have to measure. To do the measurements, we have to know what we measure. Otherwise, the measurement does not make sense. We just get random numbers without any structure. So let me finish with let's say, a thought-provoking point. Okay, that was also in the talk of Professor Placek, comment at the end. So what if the probabilities are real, if the possibilities are real? So what if we really have a choice? Maybe it is that we, the observers, we always interfere with the external world. And actually, when we do science, when we do experiments, we do change the world. I mean, not its description, but the actual word. And to me, that's not because we are conscious, but that would be rather because we are massive. But because we are conscious, we can make it maybe a bit smarter. But say on the philosophical point of view, maybe it would be worth to think of a kind of active ontology, which does depend on the observer. It takes into account the Heisenberg cut, in a sense. Thank you for your attention.